Alright, so let's go ahead and finish part 2 of the Unit 5 video. So we're going to continue talking about momentum and impulse. So I ended the last video talking about energy and power. And one thing I want you to keep in mind that energy is a scalar, right? So it doesn't have a direction to it. But once we start talking about momentum, momentum is actually a vector. It has a direction. So the variable for momentum is a little p, and momentum is your mass times your velocity, and the unit for that is kilograms times meters per second. Now, and this does have a direction, so make sure that if you are adding different momentums, you take in consideration the velocity, which direction the velocity is, if it's positive or negative, or if two things are going in opposite directions to give them, opposite signs. Right, so if we want to, just like work changes something's energy, impulse changes something's momentum, or it's a measure of the change of momentum of an object, right? So the change in momentum, the equation for this, the change in momentum, and really this comes from Newton's second law, which remember is force equals mass times acceleration, and we know that acceleration is velocity over time, so we could also write it like this. So really this is just Newton's second law, again in a different form. So impulse is force times time is equal to the change in mv, or the change in momentum. So units that we have for impulse, which is weird, impulse is a two-variable symbol, right? So we have force times time, so the units that we can have are newtons times seconds, or we can also have, because it's the change in momentum, you can have kilograms times meters per second, right? So if we kind of think back to what work was, because we're kind of likening impulse and work, we said the unit for work was joules, which because it's the change in energy, but it also is force times distance, so it also can be newtons times meters. So you can kind of think of these things sort of similarly. Right? So when you apply, when impulse occurs, really sort of the idea behind impulse is that you can exert a force in order to change something's momentum. And that force can happen instantaneously and change that. It can be a large force that happens very quickly that will change the momentum within a very short period of time. Or it can be a force that is spread out and changes the momentum over a period of time. And in this case, you would never exert a force all at once. That would be great enough to damage something. So we, look at the idea of an egg. Like if you threw an egg against the wall, it would smash because all the force of the wall is being exerted in order to change the momentum of the egg is being exerted like instantaneously. Whereas if we threw that same egg and it hit something that had some sort of elasticity to it, like a sheet, then that force, in order to change the momentum of the egg, instead of all happening at once, would be spread over at the time period that it took for that object to move, right? So, graphically, when we're looking at impulse, quite frequently, we will have graphs that have force in time, and as a result of force in time, if I were going to graph it like this, or if I were to have a graph like this, because of the equation for impulse, we can quantify the change in momentum as the area under the curve for this. So just like in our, as we discussed energy, momentum is also conserved. So in terms of energy, we said that energy is always conserved, but it's not necessarily always mechanically conserved. We can lose energy from a mechanical system to other forms like thermal energy and friction. However, momentum is always conserved. Right? So momentum is always conserved. So if I have a scenario in which we have a object going and colliding with another object, right? I can determine like the relative velocities of different objects as they move around because momentum is conserved within that system always. So we have different kinds of collisions. We have elastic collisions, and we have inelastic collisions, and we also kind of talked about this idea of like what is essentially like an explosion. Right? And in every single case, momentum is always conserved. And an elastic collision, if something is said to be perfectly elastic, right? Perfectly elastic means that kinetic energy is also conserved. Right? So this only occurs in perfectly elastic collisions. In every other kind of collision, we're going to have some loss in kinetic energy and some degree of what we say is inelasticity. So when we do problems that involve conservation of momentum, we need to just do like we did with the conservation of energy equations, and we need to figure out, okay, what was the momentum before or at the beginning, and what is the momentum after. And this point right here, the equal sign, is some sort of collision or change within the system, right? And so before, you might have more than one object within the system that has momentum, and then after, you might have only one object. Or maybe you have only one object at first that has momentum, and then after you have two objects that have momentum. Or maybe you have two objects and two objects. It doesn't really matter. Every single time you do this, it's going to be the same kind of scenario. So let's just do a few examples. Right? So let's say you have one cart and it's kind of moving along with some velocity, and it has some mass, and it encounters another cart that has a velocity that's equal to 0, right? So it comes along, it's going to smash into this thing, and they stick together. Right? So if they stick together, then together they're going to move off in some direction over here. So this is my before and this is my after. So to do a conservation of momentum equation, well, over here I only have the momentum of this object, and so that must be equal to the momentum of these two together. So we'll say m1 and m2 times v, because they're one object. Right? Let's say they bounce off one another. So here this guy comes along, and let's say this one is moving in this direction, and they hit each other and they bounce in opposite directions. Goes this way, another goes this way, right? So at the beginning I have two objects that have momentum, at the end I have two objects that have momentum. And they are going in opposite directions, so that's where we have to pull back that idea that momentum is a vector. So we would have m times v for this guy, plus m times v for this guy, but we would want to make one of these negative, right? Must be equal to the m times v of this guy, and just because their arrows are pointing in the same directions, we know that this would be negative, plus the m times v of this guy, right? Now, if we have an example of an explosion, let's say two cars are together and they're not moving at all, and then we use a plunger, and after the collision, they move off in this direction and this direction, right? So initially, the velocity is equal to 0, so over here, our momentum is 0. That means over here, that must be equal to the momentum that this thing has plus the momentum that this thing has, right? How can two numbers added together equal 0? Well, remember they have opposite directions, so they would have to be equal and opposite to cancel out, and one of the v's would have to be set as negative. Right? So this is conservation of momentum, and really you can just apply the same exact concept. Just think about what's happening before and what is happening after, right? What are the objects that have momentum at the beginning? That must be equal to whatever objects have the momentum at the end. Sometimes we have multiple objects. Sometimes those objects stick together. And then if you just think about how they're moving, if they're moving as one unit, then we can treat them as one overall mass.